this is not the case, then let's stick to the chat for more questions. So the next speaker is Bernd Scheele. Bernd is the Max Planck Director of the Max Planck Institute for Informatics in Saarbrücken, Saarland. And he is the head of the computer vision department. So before that, Bernd was a full professor at TU Darmstadt. He was an assistant professor of ETH Zurich and stayed at MIT and CMU. In the interest of time, I give the pointer to Bernd. Bernd.
Yes, hi. I hope you can hear me. Thanks very much for the invitation. I'm very glad to be here. It's really a nice workshop in a really important area of being safe for autonomous driving. And I guess the two topics I want to talk about today are essentially robustness and interpretability. The first one really is about, it's very close to autonomous driving, actually. It's about sort of if it's good or not so good, actually, to using scene context, and I will get to this. And that's actually all Patrick already said. There is sort of an important part of that theme here is how or if we can validate sort of methods that we are actually using for autonomous driving really in the settings of the autonomous driving. So this is really the first part where we had a series of papers. And the second part will be more about interpretability, where this is not directly yet related to autonomous driving because we haven't really used yet this for autonomous driving, more for really image classification. But still, interpretability is obviously a very, very important topic also for autonomous driving. So I think it's really worth sort of looking at this and discuss this a bit. Right. So the first part, as I said, right, is about sort of the good and bad sides of context for various tasks and also in autonomous driving. And this is work actually from Rakshit Shetty. He's a PhD student and he's co-supervised by Mario Fritz and myself. And what is this problem really about? So if you look at a scene like this one here on the left, right, for example, you have an original image and you take sort of a state-of-the-art image segmentation network, you're actually getting sort of very good segmentation. So here's the road, here's the cars, the sidewalks, building, and so forth. You're really getting very good performance on these things, right? The numbers are going up as we speak, right? In particular, when we have sufficient numbers of training data in principle about these kind of settings. Right, but here actually in this scene, actually things actually start to go wrong. And what we did actually in this particular scene, we just take this scene here and we have an algorithm I'm going to talk very quickly about this, is how to remove the cars on the left side of the road. And now once the cars on the left side of the road actually are gone, you will see actually sort of, you know, the road is still there, the building is still there, actually, but the sidewalks on the right, all of a sudden is not really seen anymore by the algorithm, right? And that actually is a problem, right? That you actually now, all of a sudden, this becomes part of the road, at least partially here, for autonomous driving. So why is that actually the case? And actually the reason is that it's actually in this particular image, it's very sensical that if there are sort of the context information of cars parking on the left side of the road, it makes a lot of sense that the likelihood is quite a bit higher that the right side of the road, there is actually a sidewalk, because that's probably more of a street scene type of thing, a city street type of thing, than sort of another type of scene, right? We really expect there being a higher likelihood of sidewalks. And this context information can be extremely valuable, obviously, but it can be also, as in this case, quite sort of, you know, disadvantages for the output of the algorithm. What we want to do is really sort of getting over this. And what we try to do in the first place is actually we try to basically quantify and this kind of context dependency in the aspect that we looked at actually is core occurring objects. So we really deleted, let's say, the cars, as I said, right, and see how it actually influences other parts of the scene. And as I said, there's these two goals. The one is the quantification, and that's really so for validating the problem, right? If actually our algorithm is working in sort of scenes that we really are finding important for our algorithm for autonomous driving, for example, but at the same time, really sort of, you know, might not work well in us. And then sort of the second part, once I identified those settings or context issues, I can actually start doing data augmentation to hopefully obtain better performance. Again, here's another example here. Again, here we removed from that particular image, we removed the cars here on the right side, the lower right part of the image. And as you see, sort of here, it's probably set before, while the cars were still there, that there's a road, and all of a sudden, however, it's set there's a sidewalk. So these kind of things really happen all the time. And I'm going to show more examples of this type. Right. So as I said, we actually worked on this problem on how to remove objects, and I'm not going to have the time here today to talk about this. There's an entire NERDS paper just about this. But the setting is you have an input image like this one here. You just tell basically the system there you want to remove the dog, right? You don't tell where it is. You just say remove the dog, right? And you see here we're getting images that where really the dog is gone. Here the person is gone, right? Here the TV is gone, and so forth. You're going to see that this really sort of works reasonably well, right? Sort of learn sort of not in a fully supervised manner, as I said, right? So, but really sort of in a weakly supervised manner to really get rid of the these objects, right? In order to generate sort of settings that are really out of context, they tend to be more potentially more difficult to deal with current systems because they haven't seen all this kind of context settings. And so here, as I said, you do this, now you can think of really doing an automated testing framework, right? By basically removing sort of 1 or 2 objects at a time. And by this removal, right, sort of look actually how well your model does. So in this particular case, right, so here in this image, here we removed on this, on the right side, we removed the monitor. In the middle, we removed the keyboard. And here on the left, we removed the mouse. And now you're looking actually how good your system is still doing. And actually, if it is doing well, right, you're fine. But if it's not doing well, you basically add this to your data set as a data augmentation. You retrain your model, and you can use obviously until you don't really find such cases anymore. Right, and here we just that's the gist of the idea. And here I'm going to give you some examples which we hopefully make the point that this is actually really sort of an interesting setting, right? So here we have again this image I had shown before, where we remove the cars here on the right side of the road. The original sort of OpenNet here, in that case, really is failing. But then if you're starting augmenting the data with this, new context situations where actually original model was failing, you actually do better here eventually here, right? So in our setting. Right, so then here, if you were, again, another image that I showed also before, here taking the left side of the cars here on the left side of the road, right here, if it's removed, right, UberNet actually starts failing, as I showed before. If I do this sort of analysis and augmentation in the setting, in the loop, essentially, I can really sort of recover, most of the site work, successfully. And then actually, let me show you 2 more examples, which, this one here I find striking because it really is showing how much your context is, in a sense, overused. Again, context is a good thing, don't get me wrong. Context is something very, very important, but actually it's overused by our systems. So again, here you take the original image, right? Here the image is edited that they're taking out these trees at the top here of the image. Now in the original case, right, you're getting here perfectly sort of grass and trees and sky, whatnot. But then all of a sudden, without the trees, all this woody grass region is essentially, classified at birth. And I find this actually a bit striking and surprising because really, if we look at this, even locally, there's no context necessary whatsoever to really sort of identify that this is grass. And still our systems are, as of today, basically using this. They're really overusing the context, I would argue, because locally you really could decide this is grass and I don't really need to know that there's trees on top or something, right? And this is not a unique case. These are really sort of pretty prominent. And I'll have here, once again, retrained with data augmentation, I can actually lower this issue. And then maybe this example is maybe the one that is closest to the discussion we have here in terms of autonomous driving. Again, oops, something is rough here with my mouse. Oops. Sorry, let me check. Anyway, so the top left image. Can you still hear me? Something is off here. Somehow my computer.
Yeah,
okay.
It looks like you got another mic, but we can hear you again.
Okay, sorry, something is not working here. Okay, so I have my mouse here again. Okay, so in the upper left corner, you see this image, right, where we have this car on the street, right, in a winter scene. And then if you remove the car in this winter scene, right, all of a sudden what you'll see is actually sort of things actually go pretty crazy here, right? So we still have a bit of road here on the right side, but here on the left, we have water and earth and stuff. And now this is actually, if you think about it, right, so these kind of settings, right, we can't, this is a pretty sort of specific, winter kind of scene with a particular height of snow on the right, on the left, right? Trees are snowy, street is sort of dirty, as we know it can happen in winter time, right? So using the car to see the road is perfectly fine for a system to make the decision, right? Because obviously, as soon as there are cars, it's very likely there's a road. However, if you take away the car, right, then all of a sudden it's sort of the system is more blind. It actually doesn't see the road anymore, simply because it overuses again the context, right? We're really now in this tail of the distribution where we tend not to have sufficient amounts of training data, and then sort of our systems tend to start failing. So this is a classic way, a classic setting where we want to validate our systems by actually really sort of augmenting the data and seeing what are the failure cases are. So obviously, again, right, if I add those failure cases into my system, I can sort of overcome them at least to a certain extent. Okay, so then there was actually one next step we did in this line of work, where we now really, again, it's really about autonomous automated testing and robustification for semantic, what we call semantic adversarial data generation. What I mean by this semantic rather than standard adversarial data generation, I'll come to this in a second. But again, the story is that when we're working on IID data, sort of independent, identically distributed data, then if you do train and test, right, we are having a pretty easy way actually of doing things. But often, right, so if you have context changes, domain shifts, we really want to do actually in the tail of distribution, which actually is really hard often for these models. So there is, cases, again, I showed sort of cases where we have context changes that other work in this space. If you add noise or something, we're really sort of going to have trouble to really recover the performance we want. So the bottom line of the story really is that, if we only use IID data for training and test, we tend to completely overestimate our performance, right? So it's really, that's a classic thing. I mean, if you ask lots of people, right, sort of about ImageNet training, all these 1,000 classes, do they work? Sort of, do they really work on all kinds of other classes? Obviously, it doesn't, right? But even still, it works on the IID sort of test set for ImageNet. So really, this is a classic kind of problem here. So the way we're thinking about this is actually now, rather than just doing sort of a random search. The prior work was really a bit of random search, right? We basically removed the car, we added a car, right? We did this kind of thing. We basically modified the scene in order to find this kind of difficult cases. Now what we want to do is you're starting from the training data, and we're literally doing a gradient descent in the model space, essentially, right? To generate sort of images that are more and more difficult for the system until we basically cross the model boundary, right? But potentially not yet the true class boundary. So here, this is really a horse, right? Obviously for all of us. So here we generated an image that really looks roughly like a cow still, but actually our system already thinks it's a horse. So that's why we're calling it semantic adversarial training, right? Generation, because we're trying to do this within a sort of a space that actually this still remains sort of roughly sort of the kind of class. And how do we do this is basically we have this model, and again, I can't really give all the details, but the idea is you start with an image, right here of a bird, right? Then you have a synthesizer, which basically for a particular part of the image, basically can generate another bird image, right? So in this other bird image, actually the way we constrain it is that we're having a latent space that we learned during the overall training of the model. In that latent space, we're looking at the convex hull of examples of our class, in this case birds, which actually means that we're really staying within roughly the semantic space of those birds. There's no guarantee, that's for sure, because it's just a convex hull and it might be not working perfectly, but it's still, as we will see, right, really is quite convincing in many cases that actually really stays in there. So then we have a synthesizer for this, so that's just staying within the class that we are having here. But then we're doing the classic adversarial setting where we now have a detector, right? And the loss, we basically want to increase the loss for the detector, basically giving it the wrong detection. And then basically you're updating this until we really sort of have a different classification. Okay, so let me show you here an example here. We start with this bird, right? And you're starting to basically generating, more and more birds here. And eventually here at this point, all of a sudden becomes a dog for a classifier, right? With a very high confidence, 0.8. Right here is even more confident about the dog and sees even the frisbee right in the middle of the dog, and here even right slightly more. So that's the idea. And for us as humans, clearly this is still a bird, right? Yes, there's artifacts, I agree, because the generators today's are not really perfect, but still it is sort of a failure case, right? And now a human should look at this and say, no, this is really wrong, right? And that's obviously also augment your data, your system again with this kind of generated cases in order to basically improve your performance. So let me show you just sort of some numeric numbers. First of all, right, so in the original data, we have some mean average precision here, right, of 81, right? If we basically replace one of those objects, we're dropping this to close to 60. If you replace two objects here to 46 or so. And obviously you saw these artifacts in the images, right? So we made a user study. And when users look at this, right, they still said 93% of our images that we generated where they started these things fail, basically were sort of, still really from the same class. So really, there seemed to be sort of some reasonable quality in here. Let me give you some images here that what kind of things happen, right? And what kind of semantic adversarials we're finding in this setting. So here we start from this stop sign, right? And then get the semantic adversarial generation, we're getting this kind of camouflage stop sign. So now you can argue, oh, well, that's obviously not a stop sign anymore because it's black, right? Or close to black, but it could be very dirty stop sign still, right? And we would still expect an autonomous car to detect the stop signs, at least in my opinion, right? So in that sense, it is something that we probably want to take care of. So here's a case which things are just, going completely wrong. So we're starting here with the motorcycle, and then we're changing the appearance here, and all of a sudden it becomes a backpack, right? And I think this is just, unacceptable in this particular case, right? You want to really being able to detect the motorcycle here, rightly so. And this is a case which again is a bit about context, actually, right? So here you have a skier up in the air, and you might argue that's not very relevant for autonomous driving, and I would agree. But then sort of here, if you change the appearance, right, it becomes an airplane where basically this context of something in the air is probably more appropriate, right, in the air, and then sort of airplane seems to be canonical case. So here's actually an interesting table where now you want to evaluate and see how much you're doing better, right? And if you're going to, actually we did this across a number of data sets here. If you look actually at the IID test set, right, you're doing only slightly better, which is interesting, right? Because the IID data, right, is sort of the best case for the IID trained model. Right now we're having a model here that's really is trained on non-IID data, right? And it still does improve a bit on the IID data still. But actually all the kind of cases that you really are improving on, there should be really are mostly not covered here. So if you go to this out of distribution kind of test sets, which are again generated by sort of people trying to have sort of a different kind of context, then you're basically, you're seeing more improvement. But I would argue there's more improvement actually than these numbers show, simply because these kind of test sets we don't really have that are really sort of are relevant for all the kind of cases we need to do. Okay, so here, yes, I talked a bit in this first part about the bright and dark sides of scene context, right? We post a new testing framework for data augmentation to really automatically generate diverse and different scene contexts, and then sort of hopefully overcome some of those dependencies. And then we also had this new semantic adversarial framework in the last bit. And I think, right, this is sort of just the beginning of the work. We really need much more work in this space to really move forward. Yes, and then, in the time remaining, let me actually also talk about the second piece of work, which is sort of this CODA net, which is really about interpretability, right? In that case of convolutional neural networks. Right, so this is actually work from Maurice Böhler, and he's co-supervised by Mario Fritz and myself. That actually will be presented at CVPR later this week. So what is this, the bottom line of the story here? The bottom line of the story is that when we're looking at sort of deep neural networks, right, we are basically, for the most part, we're only looking at the accuracy, right? We're really trying to improve accuracy. This kind of works that we're having here, right, is the right thing to really focus on other things like safety and security of these kind of models. And obviously, these models are to a large extent black boxes if we know obviously all the computations inside, but it's actually not really sort of clear how they really can get to decisions. And then actually, obviously, yes, there's ways to try to explain things, what's actually going on, and these are basically derived post-hoc for the most part. And here I'm showing sort of examples. Classic things like, for example, in the middle we have GradCam. Here in the front we have kind of gradient-based methods. There's Lime and Rise. All these things are basically used to understand what the network does, but it's all post-hoc, right? And the kind of idea we have, what the goal we have, is really to have interpretability as well as having good high accuracy, right? But having interpretability as a first citizen in this design of the network. And what you see here is basically this kind of explanations we're getting or interpretation of our network, and you see they're quite a bit more detailed, and I would argue actually they're more faithful, and the way I'm designing this network, they actually are literally faithful. This is really that kind of information that is used by the network for achieving the final result. Okay, so right, how do we do this? Right, okay, so there's an input image, there's some classification model here, and then we obviously want a classification, but at the same time we also want to get sort of a explanation, interpretation here, what's going on. And the way we do this is really this so-called CODA networks, you go Convolutional Dynamic Alignment Networks, which are essentially deep neural networks, but they're having sort of design principles to really set them apart from standard networks. So here's, it's the CODA network really is also sort of a set of multiple layers, so that's actually not very surprising. But actually, the individual layers are basically having particular properties. Now, really two main properties. The one is what we call dynamic linearity, and the other one is boundness. What does it mean, dynamic linearity? So first of all, sort of here, the output of a layer, sort of think about sort of the first layer output basically is literally a linear transformation of the first of the image, of the input of the first layer. However, this linear transformation, this W here, is actually dependent on the input. And actually, it is such that it's actually in a non-linear dependent on the input, which means at the end, you're still getting sort of a performance sort of output here that we can be used eventually for classification. But still, the mapping here from the input here to this, from the input, from the first layer to the input of the second layer is still linear mapping at the end, which means at the end, you really have a way to really see what exactly is used because the entire network has linear mapping. So that's really the first thing. So here's basically, if you have a particular output, you have just literally a scalar product, right, as it is classic in sort of linear mappings. And then the second part, and that's actually really important, is also that it's actually bounded. So each of those scalar products, so these W's, these rows in this matrix are actually bounded, right? They actually have a norm of 1, right? That's set by during training, we're setting that to 1, which means they're really bounded. What does that help us? Well, if you think about it, right, if you have an input here like the X here, right? And if you want to maximize eventually, right, through the entire network, you want to maximize the output with a scalar product, what you have to do is essentially you have to align basically the W here directly with sort of the input, which means that's why we're calling them alignment networks, because they have a high pressure to align in order to maximize the output. And again, the reason is why this is the case, because the W's themselves are bounded. X obviously is static, that's the input, right, respectively, which means, the best way actually to get the high output is actually by trying to align these two vectors. Okay, so since this is obviously the case not for a single layer only, right, but it's actually, really is for the entire network, it's inherited here. All of this is really dynamic linear from the input to the final output, literally the final output, right? And it's also bounded, right? So these things are basically given by these properties. And now when you're looking at these visualizations, just to make the point, so this really is the visualization. This is now this is how the logic eventually is generated for a particular class. And the logic is basically you just look, if you just sum over the entire image, you would get exactly the logic for that particular input image, right? So that you do this for all the classes, which means now for a particular class, you can say exactly which part of the image were really used to generate your outputs, right? And what we visualize is exactly these kind of pictures here to see which parts of the image were used, right? And again, the matrix itself, obviously, then it's bounded, and because of that, because you want to maximize the output eventually, you're basically getting really, the discriminant features are used in this matrix. Okay, so let me show some results. Again, first of all, here's some qualitative results, and as you see, right, as I mentioned before, they're quite detailed, and again, they're really sort of faithful to the mapping, because again, this is exactly what's used to generate the logic, right? If you sum over the image, right, all the pixels that are visualized here, you get the logic exactly for that particular class. So it really is faithful to this thing. Now, if you're looking also to quantify the performance here, if this actually also does better than other interpretability methods, there is sort of the two ways you're evaluating this. The one is the so-called pointing game. You have a 2x2 image here, where now you want to basically explain, right? If you get, for example, the airplane, the upper left corner, you get this basically as an output, right? Where does the evidence come from? Is it in here? It comes from the upper left part. So you can always look actually how good is that part where there really is the information for the plane versus the rest of the image, the other 3 blocks here, right? And then basically look actually how good you are in this. And if you look at this, that's called the localization matrix. That's not something we invented, as somebody else talked about. As you see here, so some of the gradient methods are not that great actually, because they're getting gradients everywhere in the image. Our method basically really gets very good performance here. It's a lot better at, for example, as GradCam actually, right? Which is really what a lot of people use, and still really this localization is quite a bit better in our case. And there's another way basically to trying to evaluate these interpretability methods, which is what we call the pixel removal metric. So we basically be taking out the unimportant pixels. You look actually where the least information came from. You take them out, right? And if you take them out, right, you actually either expect them to go up or at least stay constant, right? And again, our methods, the light blue one actually is again outperforming the other methods by quite some margin. And right, so let me just obviously, accuracy is also very important, right? So here we are showing results, for example, on cipher 10, right, where we are comparable with the ResNet here, essentially with a really small CODA net, which is all the small CODA net has some 8 million parameters, I believe it is, right? So then here with the medium size, which has some 28 million parameters, actually is comparable to a wide ResNet, and we also are very comparable, right, to sort of to the ResNet 110 on sort of tiny image. So really, we're getting also the performance essentially, right? At least on those kind of data sets at the moment. There will be code available that's been released. Here you find sort of the that information also, right, when you look at the CBBR paper, obviously. With that, in order to leave a bit of time for questions, I'm wrapping up here. Yeah, thank you very much for the attention. I'd be happy to take any questions you might have.
Excellent, Bernd. Thank you for that. Yeah, actually, there were already some questions coming up in the chat, and actually, I also noticed that it's about the object removal or infilling. Yeah, there was one example you showed with the car in this winter scene. Yeah, although there was an in-painting, there was still the silhouette of a car visible. Yes. Yeah, here it is. Yeah, so that was a question, and I would add, isn't that so? Apparently, the quality of your detection and in-painting has an effect, or the question is how much of an effect is this? Isn't that also introducing some bias here?
No, sure. Okay, so yeah, I mean, I always forget to mention this. So we have, I mean, so there's these two parts of this game. Right? The one part of the game is we're generating images, right, to see what's going on and to data augment, right? But eventually we're testing on real images, right? And these real images are basically, they have no artifacts because they're generated. They're normal images, right? So there's really these two ways of dealing with this. The numbers I showed later, right, these accuracies, whatnot, they're all basically only on real images, right? So we're not testing on real images. This is more for highlighting cases, right, where things are basically might go wrong, right, and then once we have found those, we're adding them to the training. Again, we only have those artifacts during training, right, but not during testing. That's the key. And I should have mentioned this, but yeah.
So, does it answer the question of Alexander? He also asked about the removal, I think. Yeah. If not, there was another question from Maram on the analysis of the CODA network. Does one assume that the dependence of the weights or on the input X can be neglected in the first order?
It was like, again, the input of that depends of the weight on the input. No, in the first order approximation, I'm not sure what. So no, I mean this. Okay, so I haven't really talked about how exactly this is generated. Maybe I'm showing briefly slide about this that maybe I did, which I didn't show. So what you're doing, so a single, so what's doing, what we call a single dynamic alignment unit, right? So that's the input X here that we have here. Then we have this B times X plus B, right? That actually basically is this, what I'm showing, this is still a linear mapping, right? It's still a vector, right? Which you're generating, but that actually is generated non-linearly. So in that sense, I'm not sure how I would be able to approximate this or sort of neglect right in the first order. So it really is, it's a proper linearity here, right? And actually that's key to success, to really having a linearity here involved to basically have this this mapping sort of to be powerful, right? Again, you're still getting, high performance, right, on this data set I showed. So in that sense, we have to have this. I mean, I wouldn't see this can be, if it were approximatable by a single derivative or something, right? We would again have basically only linear mapping, right, from front to end, which we know is not performant, right?
So maybe one more from Patrick. Patrick, are you still online? Maybe you can ask by yourself.
I guess I don't know if you can hear me well. I think it's been already answered on the first part about the realism of the modification.
Okay, that was also the in-painting. Okay.
But Patrick had a second question, right? So about the explainability.
Yeah.
Yes. Yeah. So let me, because I think this is really critical to maybe I wasn't clear enough on this. Let me just show that slide again. Right. So as I tried to say on this slide here, so this, I mean, what we're showing here, as I said, right, if you're, I mean, at the end, right, you have sort of here at the end of the network, you're having so the logits for the different classes. Let's assume there's 1,000 classes, you have 1,000 logits, right? For each of those logits now, for this logit, you can really sort of ask how was that generated, right? And how that was generated, you literally, this is the image you're showing, you're just taking, literally marginalizing all the numbers, right? All those numbers, and you get the exact logit. right? Because this actually is, it's really what you're showing here, that's the multiplication of the W with the image, right? So that's what we're showing is really this W times the image. That's what this is, right? Except we haven't done the summation yet, okay? Right? So that's why you really see which pixels are used. In that sense, it's, I think it can't get more faithful, because that's exactly how the logic is generated. There is no supervision. The supervision is really, it's really the, you have this, how to say, as I tried to say here in this one, right? So the key actually for making this work is really this boundness, right? The one is the linearity, because we are understanding what a linear is, but this boundness basically, right? And I was trying to say this in order to maximize eventually the output for each layer and eventually the logic, right? It has to actually really align, right? We show this in the paper essentially also, that this really is probably what it needs to be done, but it's by the constraint that you have a bound. Like one thing I haven't talked about, not to complicate things, we also have a temperature parameter eventually, where we even increase basically the sort of this alignment sort of pressure to the network, right? And the more we have this, the more actually these visualizations become really not distributed as it is in ResNets, right? In ResNets, you really have sort of a very noisy distribution, because it's piecewise linear. You can still show linear mapping here, but because of this, pressure to align, we're basically really aligning with all the necessary information that is relevant for this task at hand. So it's really, the network has to do this, right? And that's actually, I have to say, it's also a bit harder to train. It's not like it wasn't like trainable immediately out of the box, right? So there is this trade-off a bit here, right? So, but actually, we have a version now that really trains, right? And really has this, explanation for the images.
Okay, thank you, Bernd.
Okay. Sure. Okay, I think we have to move on.
Sure.
I see still some questions coming into the chat. So Bernd and also Patrick, if you still have time to answer them, that would be great. Otherwise, let's give our keynote speaker a virtual applause.
Also for Patrick.
Patrick and Bernd, thank you. Thanks again.
Thank you.